Good morning students. In today's class we are going to see some applications of this relative motion. Already we have seen some numericals regarding these types of this type of case relative motion. That is, we have already worked out some numericals regarding this relative motion. Today we are going to see how we are going to apply those formulas. Okay. In relative motion, coming to this relative motion, we come across in so many ways. Suppose if we are sending a rocket to the space, we have to consider the movement of that one relative to Earth. That is, Earth is moving, it is also moving. And suppose if we are crossing a road or if there is a junction, then one vehicle is coming towards like this and another vehicle is coming in towards the same point. But while they are coming or approaching, okay, it is difficult to judge the velocities of those things. That's why they are going to use speed breakers at those points, okay, because they are going to slow down them. In this way, we are going to apply these types of things in so many ways. Now, we are going to see the boat and river problem. That is, a river is flowing, then in that one a boat is traveling. Generally, we consider the travel in a perpendicular way, and also it is associated with the velocity of water also. That is, the boat is having both its velocity as well as the velocity of water in that river. Okay, in that case, we are going to apply this sort of simple formula. We consider this one as a river, and the river is flowing like this from west to east. Okay, and boat is crossing this river from starting from point A and ending at point B. That is, it is straightly crossing this one. Then, in order to do so, how it has to travel? As the river is flowing like this, it should not start like this. It should start with some angle with this one. Some angle in this one. Okay. Then, see here, boat crossing river in shortest path. We consider U as velocity of river water or velocity of water in the river, B velocity of boat, A, B are opposite points on the bank, W is the width of the river. Then, in order to go from this point to this point, it is traveling a distance of W, where W is the width of the river, and the resultant velocity is root of v square minus u square. Okay. Then, see here, v square minus u square, and from this triangle we can turn this one. Opposite side by sin theta is or theta is equal to sin inverse opposite side by u by u by. Okay, this is how we are going to have assessment for this one. That is, to cross the river in a straight line path or in the shortest path possible, it has to start at an angle. Okay, it is having its own velocity. The resultant becomes, if this is u from Pythagoras theorem, it is the hypotenuse, it is u, it is v, it is u, then it becomes root of v square minus u square. Okay. Now, the next one is boat crossing river in shortest time. Here, we take the river like this. Then, in order to cross the river in shortest time, it has to start like this. Okay. Then, this is the velocity of the boat, and the velocity of water is u. Then, in doing so, it would go to the exact opposite side of the bank. There is some travel along the direction of water flow. Okay. U is velocity of river water, V is velocity of boat, then D is drift on the other side of the bank, then D distance. This distance is the actual distance it is going to travel. In that case, the time taken is distance by velocity. Here velocity is root of v square plus u square. Okay. Now here we are having a denominator larger value. That's why this becomes a shorter term. No doubt there is a increase in this one also. In that sense also it is going to be the greatest one because its velocity is contributed only for the crossing the river. That's why this is the shortest time. Okay. I have to remember this. Okay. Another application is rain umbrella example. Okay. Rain is falling generally within the it is falling vertically. Okay. And we are walking like this. Okay. With respect to this person, generally we do the motion of the rain. Okay. Then see here. If that is the case, how to hold umbrella? Okay. That is the practical application to that one. Okay. Not only finding the relative velocity of the rain, but we have to hold the umbrella accordingly. Suppose if the rain is coming like this and if we are walking like this, we have to hold like this. Okay. That is how we are going to apply this relative motion situation. Okay. Rain umbrella example. See, Vp is the velocity of person. Generally, the person is walking like this. Towards he is going walking or running like this. Okay. Then for him, it appears to fall vertically downwards. The relative velocity of rain with respect to person. With respect to person is this one. Then we are actual velocity of rain. Okay. Then how to tackle this one? Okay. Relative velocity of rain with respect to person is relative velocity of rain minus velocity of person. Then first we draw this one. Relative velocity of rain with respect to person. Then minus Vp. We have to take the velocity of person in the reverse direction. Then okay. Then we have to hold like this. Okay. Triangle theta like this. Okay. Now from that triangle we can take theta is equal to tan inverse of Vp by from vertical towards. Don't bother about sign here because we are calculating the theta accordingly. Okay. We just take the magnitude tan inverse Vp by V R P from vertical towards velocity of man. From vertical towards velocity of man. Okay. This is how we are going to solve this problem. Okay.